Dear students, today's topic is the gauge transformations. Topic code is EMPF-S2. In electrodynamics, Maxwell equations are expressed as del square of U plus delta by delta T into divergence of A is equal to minus delta minus rho by epsilon naught. We are looking for the a phenomena or a process in which we express the fields in which the potentials U and A are gauged in a manner that the changes takes place in the U and A, but those changes do not affect the main fields. So how these transformations are taken place in those potentials, those things are to be discussed in this topic. So the U potential this is the typical Poisson equation in electrodynamics, which we have done in the last topic. And similarly, the del square, the magnetic vector potential A vector potential is given by this expression, which is del square of A minus epsilon mu naught delta 2 by delta 2A by delta T square minus gradient of the divergence of A plus epsilon mu naught delta U by delta T is equal to minus mu naught J, equation number 2. Of course, we take that epsilon mu naught means a free space as a medium, as a free space. As the B is equal to curl of A, call this equation number 3, and E is now described as formulated as minus gradient of U minus delta A by delta T. This is equation number 4. The equations 1 and 2 seem to be very complex and looks not suitable for potential formulation. However, we have succeeded in reducing the 6 problems, that is finding E and B, 3 components each, Ex, Ey, Ez, Bx, By, Bz, that makes 6 components, down to 4 components, that is U, 1 component, and A, Ax, Ay, Az in 3 components, that is U1 and 3 components of A. Moreover, equations 1 and 2 do not uniquely define the potentials. We are free to impose extra condition on U and A as long as the original fields E and B are not affected. So let us work out precisely what the freedom demands. Suppose we have 2 sets of potentials, U and A, that is U comma A, and U prime comma A vector prime, which corresponds to the same E and B. By how much they can differ, let us say A prime differ from the A, the original A, by a factor alpha vector. So A vector prime is equal to A field vector plus alpha field vector, and the U prime as a U plus beta. Beta is some scalar. We can add it to the potential U plus beta. Since the A's gives the same B, A's gives the same B, their curl must be equal to 0. Equal to equation number 3. So, but for that we should have curl of A must be equal to 0. This is equation number 5. In order to have the same field, which is the B is equal to curl of A, we must have the curl of A, curl of alpha. If we take the curl of A, take the curl of both, curl of A prime is equal to curl of A plus curl of alpha. In order to show that this corresponds to the same original field B, which is the B prime is equal to B, means that the curl of A must be equal to 0. This is the condition we apply. Hence the B prime is equal to curl of A prime, which is equal to the correction applied. Here the curl was missing, the cross was missing. So B curl of A prime, the curl of A plus alpha. This is now new potential we have added. Any change from the A plus some new potential A, so that original B is not affected. This is now the new field. So we suppose that is the new field B prime, and we have to show that this is equal to the same old one. So when we apply the curl of A to the A prime, curl of A plus curl of alpha, since the curl of alpha we have already given that must be equal to 0, so B prime is equal to curl of A, which is equal to original B. Hence we prove that if we add any make a change in the potential, vector potential, it will not affect the original field B. We can therefore write that or predict that the alpha is the gradient of lambda, some scalar quantity. Since the curl of alpha is equal to 0, means alpha is some gradient, just like we have in the previous that the gradient of the curl of a gradient is equal to 0. So it means it is the gradient of some scalar quantity lambda, as the curl of the gradient is equal to 0, or curl of alpha is equal to 0. This will correspond that it is a function of some the scalar lambda field, which is the gradient of that lambda, where lambda is the scalar potential for the newly imposed condition that alpha is equal to gradient of lambda or minus gradient of lambda. We can put that sign as well. So newly imposed condition now, after that for E we have minus E is equal to E prime, applying for the E field. E prime is equal to minus gradient of U prime minus delta A by delta T. Since U is now been taken as U plus beta, new potential, some change in taking place in the U, that is the U when has a change, and it is U prime, but with the addition of some beta scalar function. So putting that into the E prime new field, we suppose that after the change in the potential, we have putting the U here, the E as a U plus beta gradient of that. We are putting the value of U over here, U plus U prime, which is the U plus beta, and plus delta by delta T into A plus alpha. So altogether rearranging, we get the minus gradient of U minus gradient of beta minus delta A by delta T minus delta alpha by delta T. So rearranging and simplifying, we get E prime is equal to minus gradient of U minus delta A by delta T minus gradient of the beta plus delta A by delta T, equation number 6. Now this equation 6 will lead to the original field equation, original field E, if this term delta B plus delta alpha by delta T is equal to 0. Obviously it is we have already said that the change in these potentials does not affect the main fields, so it will happen only if we apply this condition that whatever the change is taking place, that will be total equal to tend to equal to 0. So we get this equation number 7. Hence the E prime is equal to minus delta U by delta minus gradient of U minus delta A by delta T minus 0, so which is equal to E, it's the original field E, E prime is equal to E. Now since the alpha is equal to gradient of lambda, putting here the gradient of beta plus the gradient of the lambda, which is the gradient, we have the delta A alpha value in this equation we are putting. So delta lambda by delta T is equal to 0, integrating the both side of the equation with respect to obviously x. So we take the D, if we take the one dimensional gradient to be delta by delta x, one dimension we take. So dx take it to the other side, d the differential of whole. If we take the integral, we can beta plus delta lambda by delta t, which is equal to some constant kt. We say this is a time dependent, where kt is a constant and may be taken as kt is equal to 0, may can be taken as equal to 0. So beta is equal to minus delta lambda by delta t. So beta is equal to, that is the value which we have found for this scalar potential u. Additional change taken place for the beta. When the original u is changed as a u prime, then this beta is taken into account. The term delta lambda by delta t is therefore independent of the position. It could, however, depend on time. Actually, we may also absorb kt, the constant, into lambda t, as the delta prime lambda prime t is equal to 0 to t kt prime dt. So now defining a new lambda t prime as above and adding to the old one, this will not affect the gradient of the lambda. It just add kt to the delta lambda by delta t. So with all this done, we have now a prime, a vector prime, is a magnetic vector potential. This is changed vector potential. We suppose that it is changed, is equal to a plus delta a plus gradient of lambda, which is equal to a plus alpha. So this is the new term which has been added. So with the addition of the new vector potential, this is suppose it will not change the main original field. It will be equal to a prime, a vector prime is equal to a. Similarly, u prime is equal to u minus delta lambda by delta t, which is equal to u plus beta. Okay, so that is the, now in adding a new something change in the potential, the vector, the scalar potential u, electric scalar potential u, so it will not also affect the main field. So where alpha, obviously vector, is equal to gradient of the lambda, and beta is equal to minus delta lambda by delta t. So here we have the conclusion. For any old scalar function, that lambda, we can with impunity, that is exemption, add delta lambda, the gradient of lambda. We can add gradient of lambda to a, provided we simultaneously subtract delta lambda by delta t from u. So you remember, when you add some the field function, which is the gradient of lambda, in a, over there you have to subtract the partial differential of that lambda with respect to time from the E field. So this is the magnetic vector potential. If you adding the field, the vector field, then you have to simultaneously subtract the delta lambda scalar, the differential of the scalar function from the E scalar field. So that is the UE, this electric potential, field potential. None of these changes will affect the original physical quantities E and B. Such changes in U and A are called gauge transformations. So remember that gauge transformation is a process or the phenomena in which whenever we add any field function to the magnetic vector potential A, simultaneously we subtract the same lambda, which is this is obviously this is a field, vector field, but gradient of some scalar. So the same scalar will be the partial differential of the scalar field has to be subtracted, so that will not affect the main fields. So this process or this phenomena is called in which we bring such changes, the E and B for the physical quantities. Such changes is being brought into U and A that are called the gauge transformations. So that is the process of the gauge transformation in electrodynamics. With this we reach to the end of the topic. Thank you.